I never knew that everything was falling through.
Okay, second video of Waves. We're going to start off looking at the CRO. Okay, what does it stand for? The cathode ray oscilloscope. Cathode is a negative terminal, and the ray that comes out of a negative terminal is an electron ray. Okay, so it's a whole lot of electrons. And what does it do? It hits the screen like an old CRT TV, those old big TVs. Hits the screen, and you can then see some waveforms on the screen. So, the CRO uses a graphical representation of a wave. The type of graph is a displacement time graph. Okay, how does it measure it? It's actually voltage versus time. Okay, and the voltage is associated with displacement. Okay, so the greater the voltage created from your microphone or your speaker or the circuit, the greater your displacement of the wave. The CRO is split up into various squares, 1 centimeter by 1 centimeter, and there are two knobs to control the most important functions, and that's what we're going to look at. So here is our CRO, okay, so this is what it actually looks like, this one down here, okay. If we use it in class, that's what you'll get, and you can actually see there's some waves on here. Where there is now, I just drew them. So, on here there's two dials that are quite important, there's that one and that one. Okay, one controls the x-axis and one controls the y-axis. So if we look at this representation here, the y-axis is the voltage and the x-axis is the time. So if you change the time, you change the spacing of the wave in terms of the period. So if we make let's say we change this thing from seconds to milliseconds, then the gap of this will get much larger. Okay, so if that's 1 second, well, it's going to get huge like that if it's going to be turned into milliseconds, because there's a big distance between the crest to crest for 1 second. Voltage is the amplitude. If we go from peak to peak like that, that's called the peak-to-peak voltage. So on our thing here, okay, we have little centimeter squares. Okay, 1 centimeter by 1 centimeter. Now if we look at this dial here, this is the volts per division dial. Volts, remember, is on the y-axis. Okay, now if we set this thing to, let's say, that value there, which is 5 volts per division, that means for every 1 centimeter, it would be 5 volts. Okay, if we change the time one here to 1 millisecond per division, okay, that will be 1 millisecond, next one will be 2 milliseconds, 3 milliseconds, and so on. So effectively we're creating just what goes on the scale on the graph. So the amplitude control, this decides how big each division in the vertical axis is, and the time-based control, this controls the rate at which the dot sweeps the screen. The settings are in seconds per centimeter. So let's looking at this CRO, and it has a time base of 1 millisecond for every centimeter. So that means if we go along here, each one of these gaps is 1 millisecond. So what is the period? Well, period could be from crest to crest, and in this case is 2.8 centimeters. So if it's 1 millisecond for every centimeter, this must mean it must be equal to 2.8 milliseconds. Okay, what's the frequency? Well, frequency equals 1 over the period, so we just do 1 over 2.8 times 10 to the minus 3. Something you got to remember from last year is reflection and refraction. We won't go into it, but just remember these are properties of waves. Okay, if we have a wave, then we can get those. Something else that's a property of a wave that we didn't look at last year is called polarization. Okay, polarized waves contain particles that move in one plane only. This only occurs with transverse waves. So examples of this are the radio broadcast, lenses, and seeing underwater. Those things are where you can see polarization in effect. Okay, if you have a look at it, a radio broadcast, usually you put your aerial vertical, okay, or something like that, or you look at a TV aerial, is usually the old TV aerials, they're usually those big things like that, okay, they're polarized because your waves come in sideways and hit your aerial in the same plane of motion. So these aren't lenses as in lenses like that. These are lenses as in Polaroid lenses, okay, and glasses. Some fishermen uses Polaroid lenses so they can see underwater easier. They get rid of a whole lot of different scattered rays, okay, and just get the rays that are coming directly from the water. So what does it really mean? Well, look at this, okay, if we had, let's find a new page, if we had a wave, okay, from light, it could be going along like this, going down the page, but it could actually also be in a different direction. It could be going along this way. It could also be going this way. Okay. Oh, it's quite hard to draw that way. Okay, so it could be going in a whole lot of different planes. So it could be going back and forth that way. Particles will be going that way, that way, that way. So this is unpolarized, okay? Unpolarized. But if we put it through some sort of filter, so all that light travels through this filter that looks like essentially a picket fence, it will come out the other side and it can be only vibrating in one direction. Okay? So really you can think about it as if you had a rope, okay, and you shake the rope up and down, you can create a transverse wave going down the rope. If the rope was going through a picket fence and the gaps in the fence were the same direction as the motion of the rope, then the wave will go through. However, if you shake the rope side to side, you'll get a transverse wave going this way, side to side, and it can't go through the picket fence because the particles in the fence there want to move back and forth and they can't because there's no gap. So that wave will actually get cancelled out. And that's what polarization is. Now light intensity is essentially how bright things are, and that relates to power and so on. So waves are a means to transmit energy. So a measure of this energy is called intensity. Light intensity is the rate of flow of energy per unit area at right angles to the direction of travel of the wave. It is measured in watts per meter. The intensity depends on the square of the amplitude. Okay, so there's a relationship between intensity I and amplitude. Okay, and it's a proportional relationship. So in other words, if I double the amplitude, I should have 4 times the intensity. Okay, so a wave of amplitude 2 millimeters has an intensity of that. If the wave's amplitude was raised to 6 millimeters, find the new wave intensity. So because of this proportional relationship, if I go up 3 times in my amplitude and I square that rise, okay, so what's 3 squared? 9. I must get 9 times the intensity. So the answer will be 9 times 50. Okay, so if I double it to 4, I'm actually getting 4 times the intensity. But if I go up 3 times, I get 9 times the intensity. Another way of looking at it is let's make this into an equals equation by putting in some sort of constant, and let's call it, what's the constant letter we haven't used? How about, let's just use a general one, k, okay, Ka squared. So, if you look at this formula, 50 will equal some sort of constant multiplied by 2 squared. Okay, so what's K going to be equal to? Let's have a look. That equals 12.5. So that is a constant and it doesn't change. So now I've got a formula that is I equals 12.5 A squared. So if I put in the new A value times 6 squared, I should get the intensity that's the same. 450. Does that match the one over there? If the wave's intensity was to now be halved, calculate the change in amplitude required. Okay, so we could use our formula we used before. I equals 12.5 A squared. The intensity was now going to be 25. Then we solve for A squared. However, if you do it logically, intensity is proportional to amplitude squared. Okay, if I want to get half I, what must we multiply A by and then square it to get a half? Okay, well, if I multiply it by 1 over square root of 2 and then square that, I get a half. Okay, it gets rid of that square root. So just be aware of that one. What's an electromagnetic wave? Well, electromagnetic wave is actually two fields oscillating against each other. So when you have an increasing electric field, electromagnetic actually tells you that if you're going to have electric fields, you must have a magnetic field. So we have an increasing electric field, we must have an increasing magnetic field. And they're always 90 degrees to each other. And that's why it's called electromagnetic waves. And there's a little diagram of that. So the electromagnetic spectrum is something you have to memorize, essentially each part of it. Last year in IG you looked at what each part of it can do. This year they just really want to test you on memorizing the numbers. Okay, so it's not very exciting. So one thing that's very important, remember that the speed of all electromagnetic waves in a vacuum is 3 times 10 to the 8 meters per second. So it's a constant. Okay, so if you ever want to find frequency and you know wavelength, well, you can easily use this formula because you know C each time. These are some ranges you need to remember for the wavelength. How do you find frequency? Just remember, use F equals C over lambda. Okay, so for radio waves, you could put in 3 times 10 to the 8 meters per second and divide it by, there you go, you got 10 centimeters, so 0.1, and you'll find the frequency of radio waves, okay, the maximum frequency. And that almost does it for waves. Okay, so the last thing here is phase shift. Now we talked about phase in the earlier video. Phase is how two waves relate to each other when you look at 2 points doing the same thing. So if we're looking at the blue wave, let's look at this point here. Okay, so that point there, where's the closest one that's doing the same thing? Well, it's on the red wave, so between the two waves doing the same thing as that one and that one. Okay, and the phase difference is that distance. Now how do we measure that distance? Well, we actually measure it in degrees. Okay, if we were out by one whole wave, okay, so there's a wave, and I was looking at another wave, okay, and I make it look, actually I won't put it there. If I had another wave and I moved it right along to here, then the distance I've moved it, so let's look at that point to that point, okay, the distance I moved it is a whole wavelength, okay, one whole wave. Now one whole wave is 360 degrees or 2 pi, okay. If a wave was completely out of phase, in other words it looked like this, okay, so the distance there is half a wavelength, so that would be 180 degrees or pi. And so it all depends on how much different it is. Okay, we'll use some of the examples in class. And that's it for waves.
I never knew that everything was falling through, that everyone I knew was waiting on a cue to turn